Hello everyone, my name is Ankur Singh and I am enrolled in analog and mixed signal integrated circuit design lab. So I am working on in my lab I am working on neuromorphic circuits using memristor. So so in this subject my final project will be on NOR gate using NMOS and PMOS. So let's have a look. So in my presentation, my content will be like I've done MOSFET, that is NMOS and PMOS TC analysis. Then we will see NOR circuit and its code. Then we will see voltage transfer curve. In voltage transfer curve, we will see a graph between V in and V out. Then we will see the transient analysis. That's it for this for my project. So now coming to the MOSFET analysis. So this is the NMOS, this is drain, this is source, this is gate, and this is body. So what I have done, this is VGS, x-axis at VGS, and this is the current, that is IDS, current flow between by this IDS. And this is like I took VGS from 0.0 to 1.2. I do the DC swip from 0.0 to 1.2, and at VDS and I put VDS constant as 1.2. So if we reduce VDS, then it will be like this something. If we increase VDS, then it will be something like this. So NMOS DC analysis is this, and I've done also for with Cadence tool. So because I did this thing because when I will implement NOR circuit with Cadence environment, then what will be the transient analysis. So that's why first I did DC analysis to find the width and length of the NMOS and PMOS. So because of width and length, current will be changed. So I choose this width and this length because here we can see it's almost 50 micro, same like this, and here also we can see it almost 110 microampere here, and here also we can see 110 microampere. So that's why I took this W by L ratio in the Cadence environment. So let's see now PMOS. So PMOS, this is source and this is drain and this is gate and this is body. So same goes to with this also, like I do the DC swip of VGS, and this is the current ID IST, and this is V like VDS, some VDS voltage, some VDS not 1.2 voltage. So same goes to with this also, like if we reduce VDS, then it will be current will be reduced, and if we increase VDS, then current will increase. So I also for this getting PMOS width and length ratio, I did the DC analysis. So we can see it almost 25 22.5. Here also you can see 22.5, and here also you can see 60 micro, and here also you can see 60 micro. So almost DC strip is same, but there is difference here only. So we can neglect this thing here. We can just see the minimum current and maximum current. So at this, the width and length is for PMOS is this for Cadence only. So now coming to the our CMOS NOR circuit. So here we can see there is two input, that is in 1 and in 2. So this is our two input, this is two input NOR circuit. So this is input 1 and input 2, and this is from here we will take output. Then we are using two PMOS and two NMOS. So this is the PMOS P1 P2, and here it's NMOS. Then there are three voltage sources. I mean here VDD is also one voltage source. Then input, here also we will at input 1 and input 2 we've also put some voltage source. So that's why here also we took that source. So 1 2 3. Then coming to the capacitor, so here we use for capacitor for discharging and loading the voltages. So here also we use capacitor. So now let's see the truth table of the NOR gate. So as we know that input 1 is 0 0. So in the NOR we should get some output like 1, then 0 1, it's coming to 0. So let's see for one case, like let's see for 0 0 and 1 1. Then for 0 0, input is 0, input 1 is 0, input 2 is 0. So at that time P1 and P2 will be on. It's like for NOR circuit, it's like switching. For if we using an NMOS and PMOS in digital circuits, then we just consider on and off thing. Like this is off and this is on. So like that, like simple switches, on off. So same, like if P1 input, like for PMOS input is 1 and input 2 is 0, so both are 0. So at that time P1 and P2 will be on, and input and this NMOS N1 and N2 will be off. So at that time VDD is directly connected to the output. So at that time capacitor will be charged and the output will be VDD. So we can see at 0 0 it output will be 1, and if it is 1 and 1, then it will be, this PMOS will be off and these NMOS will be on, because in NMOS we know that if it is one output then it will be on, because of VGS is greater than that, VDS is greater than VGS minus VT. So that's why it will be in active region. Like here also I can tell one thing, that this is like some triode region and this is some active region. So like that it will be in active region at that time, so that's why it will be on. So these two will be on and these two will be off. So the ground will be connected to the out, so at that time it will be 0. So this is, and you will get 0. And same like this thing also, if we take any case between 0 1 and 1 0, then P1 is 0 and P2 will be 1. And here also we can see input 1 0 and 1. So at this time this will be like 0, so it will on, this will be on, but this case should be off. Let me erase everything, then yeah, now input 1 will be 0, input 2 will be 1. So same goes to this also. Yeah, now this will be on, but this will be off, and this also will be off, and this will be on. So we can see VDD is coming up to this, but after that it can't go because this transistor is off. But and here also we can see this is off, so ground can't go up to the drain. So and here it's on, so ground that is 0 can go. So from here we will get output is equal to 0, and we can see output is our 0 in our NOR circuits. So now coming to our physical model for each transistors, like they are dependent to something, they are independent, like for NMOS and NMOS2 and PMOS2, everything like mobility and ring combination. So mobility is like how quickly an electron can move through a metal or semiconductor when pulled by an applied voltage. So this is the mobility. And recombination is that electron pair hole, when electron and hole disappear, that is they combine. So this is called recombination. So this is simple definition. They call just when electron and hole just recombine. So that's why they call recombination. So these datas we will use, this like property we will use with our NMOS and PMOS. So now coming to circuit implementation with the G device code. So we can see we initialize the circuit with this function, and then we written some code for initializing the each transistors and every node. So we can see node GND is connected with ground. So GND means this, like if we will write anything GND, then it will be directly connected to if we will write GND, then it will directly connected to the 0 node, that is ground node. Then coming to the NMOS one. So for the NMOS one, that is this one, you can see source is connected with ground. So source will be connected with ground. Then NMOS1 gates it is connected to the input 1. So here we can see gate is connected to the input 1. Then drain, here drain is connected with output. Here drain we can see that it is connected with output. And NMOS body, it is connected with ground. Here we can see it's connected with ground. So same goes to with NMOS 2 also. Then coming to the PMOS 1 and PMOS 2. So PMOS 1 and PMOS 2, it's slightly different because it is connected in series. It's look like a series, and NMOS and NMOS 2, you can see it's look like a parallel. So it's almost structure is same for NMOS and NMOS 2. But for PMOS case, we can see here it is source. So source is connected with the VDD. Here we can see it's connected with VDD. Then other, like in PMOS 2, we can see source is connected with V1. So V1 is this. I took some node name V1 as a V1. You can choose anything, it doesn't matter. So it's a V1. And then PMOS 1 gate, it is connected with input 1. Here you can see, and PMOS 2 gate is connected with input 2. Then it's drain is also connected with V1 for PMOS 1. So these two are now connected. So that's a this is node and this node, they are now connected, source and drain node. And this drain, PMOS 2 drain, is connected with output, and PMOS 2 body is like both body are connected with VDD. So our NOR circuit is whole complete with this much of code. Now V input 1, that is which like there are, we use 3 voltage source. So now we will connect that voltage source with these input 1 and input 2 and VDD. So this will be our like voltage source, like this. It will look almost like this. So this ground, that is 0. So this 0 will be connected to ground, and this voltage source, it will be connected to the input 1, input 2 and VDD. Like there are 3 voltage source, so it will be connected separately. So these are the V input. This will be the whole command for the voltage source. And then capacitor is this. So capacitor contact 0, that is this pin, this is connected with ground, and other node, it is connected with output node. So that's the. And also, like if we generate CGNS file, we like there is some command for generating CGNS file, and we have to write that code in the file. So we can write that command in like this, like that we can generate the CGNS file of the P1 and like PMOS and NMOS. So we can't generate whole circuit CGNS file. So I just separated that, like I just put PMOS CGNS file here, got here, sorry, CGNS file, and P2 and same goes to NMOS. So it's look like I just plotted this thing. I just plotted this thing and just connected whole things. So this it will look like this, and it will look like this, that thing with CGNS file of the NOR circuit. So now coming to the law. So like we use like equilibrium law. So this is the for the equilibrium law, like Poisson. So the Poisson for NMOS 1 and NMOS 2, everything should be defined in the equilibrium law, and these are some equations that are inbuilt in the G device. And same goes to with TR law, something like TRA laws or TR law we can pronounce. And it's something like we can write here, we have tried timer. So it is with only transient analysis. If we are using transient analysis, if we want to do, then we have to define this this one line of code in our file. And if we are using if we want to do only DC analysis, then we have to just write this line of code, not this, if we want to just do DC analysis. So every other equations are same, like Poisson, E continuity, H continuity, contact. These are repeated for every NMOS and PMOS things. So these are some predefined equations in the G device. So we just write that type, and it will automatically compute inside the simulation thing. So if we want to DC analysis or transient, then we have to write this. In transient analysis, there is one difference, that we have to introduce one timer function also, that is time function. So this thing for time function means in transient analysis, as we know that x-axis is transient, x-axis sweep with time, so that's why there is a timer equation, and this will be some like current or voltage, something like that. So now coming to the bias ramping. So in bias ramping, just first, like for the supply voltage, I mean the VDD. So VDD should be 1.2. So in the first line of code we will write, if when we will do the bias ramping, so we can do that like this thing. So just do biasing voltage, biasing the circuit. So VDD will be 1.2 volt with this code, with this line of code. Then coming to, like, we have to assign some data to V input 2 and V input 2. We have to assign some voltage to V input 2 and V input 2. So what I have done here for DC analysis, we will see in the next slide what is the graph. So what I did, that V input 2 is swept with VGS, that is VG, yeah, and I will plot with output voltage, V out. So we can see what I did here, for the first, from this line of code, it will be swept from 0 to 0.6 volt, and here here we can see 0.6 to 1.2 volt, because here it's run till 0.6 volt. So here it will automatically, G device automatically start from 0.6 to 1.2, because it already computed. So G device understand this thing, so it will automatically start from 0.6 to 1.2. So I did this thing because there was problem with me, like if I just combine this thing, if I just rename, delete this line of code and directly compute compute this line of code, so there is some error. So what I have done, so I just make two intervals between that, like if the G device run from 0.0 to 1.2, so what I did, I just put some interval, like it will run first from 0 to 0.6, and then from 0.6 to it will go till 1.2. So we can introduce more thing, if you want to like if you're getting again error, then you can introduce more, like more number of intervals. It will not affect your code, but it will make your code like more smooth, I think. Like you will get more number, like you will not get any error if you put more interval. If you're getting error like at 0.6, then you can put here 0.3, then here you can put 0.9. So first it will run from 0 to 0.3, then 0.3 to 0.6, and then again from 0.6 to 0.9, and 0.9 to 1.2. So maybe you will not get error with this type of interval if you put. So I did that because I did 0.6 and 1.2, so I'm not getting error at the when I plot the DC analysis. So now coming to the transient analysis. So in the transient analysis, like first in the one code I implemented the DC for the DC analysis, and in another code I do the transient analysis. So in transient analysis we have to change something, that is we have to assign some V input 1 and V input 2. So these are the like some line of code I will show. Maybe this graph is not correct, but in the transient simulation I can show that what is the V input 1 and what is V input 2. So like this was the some code, this was some graph for this line of code, and we can after putting the V input 1 and V input 2, we can introduce more number like 8, 10 to 1.2 or 0, something. We can write more if you want to do more computation, but it will take a lot of time. So that's why I just reduced this thing and I did 2 times of this thing. So this is the you will see the transient analysis graph in next few slides. And same for V input 2, I applied V input 1, some pulses at V input 1, then some pulses at V input 2. I just applied something like that. Then we solved that circuit with our input. So I just put max step and min step something, and then I'm just sweeping the timer, that is I'm sweeping timers to 7 E10. So I just took 7 E10 at the last of data, so I just swept till 7 E10. And here also, like, I took minimum state 0.01, 0.02, 0.01 here also. But you can see in VDD, I took max step 0.5. So, like, if because VDD we need only 1.2, no, doesn't matter between that, like below like 1 or 0.8, it doesn't matter for me at in the NOR circuit. So I did one till 1.2. But here we have matter like 0. We have to plot every points. So that's why at every point from 0 to 0.6 we need every results, we need every data for that. So but here it doesn't matter, like VDD hour is 1.2. So that's the only thing we matter in VDD. So that's why I took max step here is larger here, but here it's very small, 0.002. So now coming to the DC analysis of that is voltage transfer curve. So this is our V input and this is our V output. So what I did here, you can see first I did I just differentiated both the, like I did DC sweep of input 1 and then DC sweep of input 2. So here we can see there is some little difference, not too much. So I did this thing, we can see. So this is our DC analysis, that is voltage transfer curve between V in and V out. And here I do some analysis like with 90 nanometer. So this is with 90 nanometer. Like our PMOS and NMOS are 90, area factor is 90 nanometer. Area factor we can see in this slide here. Yeah, area factor. So if we change this area factor, then the current will change accordingly, current and voltage will change accordingly. So here also we can see 90 nanometer and 90 nanometer, then it is same like that, that black and red line here. And here we can see input 1, if I choose 180 nanometer and input 2 180 nanometer, I think here red line is overlapped with another line of curve, so that's why it is not visible here, but it is like here only. And here we can see input 1 180 nanometer, input 2, that is this line, this one, and this input 2, this one. So here almost 90 nanometer and 180 nanometer, almost little bit change only. And if we choose NMOS as 90 nanometer, PMOS as 180 nanometer, we can see there is some increase, like from 0.6 it is almost on 0.6, and here it's before like lag this is like yeah, that 90 nanometer is lag with this 90 nanometer 180 nanometer. So this is our with comparison with 19 with different area factor. So with this DC analysis we can find noise margin also. So noise margin, so noise margin for a logic gate is defined as the maximum amount of noise applied to the input of each logic state while the output remains the correct state. So so this means like if we are getting, like here we can see, like for 0 volt, like for 0 logic it means 0 volt, and for 1 logic here it means 1.2 volt. So noise margin is that if we are not getting 1.2 volt, if we are getting just 1 volt, then what will be the output? So if at 1 volt the output, that logic is just 1, it means our noise margin for that is 0.2 volt, because 1.2 minus, like here VOH is, that is 1.2 volt, and minimum voltage is 1 volt. So at these, between these any voltage can come upper more than 1 volt or less than 1.2. It always our circuit will give logic 1, that is output as high. And if we are getting like 0 logic to 0 volt, and we are getting like something 0.2 volt, and it all at that time it came 0 logic 0, So this is like VIL is equal to 0.2 and VOL as 0. So at that time we are getting logic 0. So this is noise margin. What is this noise margin? So here we can see this is VOH and VIH. This is VIH, and this is for this is VIL, VOL, and this is VIL. So we have to calculate like this, like we have to calculate here that VOH minus V in VIH, and we will get the noise margin high, and we from this we can calculate VI, VIL, and VOL and VIL. So we will get the noise margin for low and noise margin for high. So like this we have to calculate noise margin. And here also we can see noise margin with Cadence. I simulated the voltage transfer curve with Cadence also. So here we can see Cadence VOH is little bit higher than the VOH of a G device, and here we can see that yep, here we can see that VOL is little bit lower than G device VOL. So here we can see G device voltage transfer curve little bit lag with Cadence G device, Cadence voltage transfer curve. And I think noise margin is almost same for both cases. Like there will be little difference between this VIL and VIH. There is only little difference, but other things will be like VOH and that NMH and NML is almost similar. Approximately it will be similar, both NMH and NML. So now coming to the gate current and 1 megahertz. So what I did here, I just put one voltage source at one sinusoidal voltage source at the input of one transistor, and at 1 megahertz, and 1 millivolt was the AC amplitude. So voltage amplitude was 1 millivolt, but DC voltage was 0 volt, and capacitance was estimated as 0.167 femtofarad. So this was like we have seen in the NOT gate lecture. So I took that capacitor value only, and I just do the simulation, and we can see that PMOS gate current is 8E3, and for the NMOS it is 2E3. So it's very low, and it was like I did the transient analysis for this also, from 4E6 to 5, almost 5E6 we can see here. So this is the transient analysis at 1 megahertz of the gate current. So now coming to our like main transient analysis of the circuit. So here we can see till 200 picofarad it's 0, and I took both graphs same because I want to change this input to, but I'm not able to because I was getting some error. So what I did, I just took one this thing and one this input and same input for both cases, and if, this here also I changed in second, and second I changed the some input 1 and input 2. So here we can see 0 0, it is coming 1. Then at 300 picofarad we can see here it's 1 1, here we can see 1 1, and at that time we are getting 0 0. So from here we can verify for 0 and 0 input that A and B is 0 0, and for 1 and 1 from here we can verify other 0 and 1 1 0. So from here we can see till 200 picofarad it is 0, sorry, and here we can see till 200 picofarad it is changing from 0 to 1. So we can see like yeah, till 100 pico it's completely 0, and there is some threshold that is 0.6. Here from the voltage transfer curve we can see till 0.6, before 0.6 it switches whole completely. So here we can see before 0.6 it will be like a 0. So this is like some noise margin type of things. So here also 0 0. So at that time it will be 1, so that is 1.2 voltage. It will start from 1.2, and if it's increased, that is 0 and 1. So 0 and 1, it will reduce. So there is also some transition and there is also some transition. So this is one thing. So, and again, now coming to the, so this is for 0 0, and then this is 1 and this is 1. So at that time it will be 0. Then there is some transition from 300 pico to 400 pico, and here also 300 to 400 pico, it's 1. So 0 to 1 it will go. So it is coming some 0 to 1, like it will be whole things, like from 0.6 it will be 0, and from 0.6 it will be 1, like if we put threshold at 0.6. So at that time 0 and 1 and 1 and 1, every time it will be 0. So that doesn't matter in this case till 400 picofarad. Farad not time, 400 picosecond. Then here it's 1, so that it will be 1. Then here again it will be whole. This is whole from 500 pico to 700, it's whole 1. And here from 500 pico to 700, if we took 0.6 as a threshold, then above that it is 1, and below that it is 0. So 1 and 1 it will again come 0, and 0 and 0, 0 and 1 it will again come 0. So this is the like whole this is the for 0 1 and 1 0 and 0 0 1 1. So the transient analysis of our, like we are putting input 1 and input 2, we are getting our result like what we want. So this is the transient analysis. And in Cadence I did for only this input. So the same like that, from 0 to 200 it's 1, and then some there is changing transition between 0 to 1, and then same input for input 1 and input 2 are same. So we are getting, and this is some, I think, capacitor, maybe because of capacitor and because of some parasitic capacitor, because and GPDK, in GPDK there is some, I think, more parasitic capacitance, so that's why it suddenly it increases. But if we like just avoid, then it will be something like that is greater than 1.2, so it will be 1. And just we can see from 1 it goes to 0, same graph like this. So I just did the comparison between both. So our input was this for both G device and our Cadence, and we can see our G device is in red line and Cadence was in black line. So we can see the transition for both, like we can see 200 pico to 300 pico. It from 0 to 1 it takes 100 picofarad, 100, sorry, not farad, it's second. 100 picosecond takes times to move from 0 to 1 volt. And same for this also, like 200 pico to 300 pico, it takes 100 pico to from 0 to 1. So from 0 to 1, like here we can see 200 to 300, it just instantly like come to at 0. So the transition in G device transistor are faster than the Cadence. So we can conclude that our G device transistor are better than Cadence transistor because of this, because of the transition very fast. If we are changing to 0 to 1, then the transition is also instantly changing from 1 to 0 in our output side. So like our transistor are faster in G device than the Cadence transistors. So we can conclude from here that our G device transistors are good and are better than the Cadence transistor. That's it. Thank you so much. And thank you so much, Professor, for your lecture. And I have learned a lot from your lectures, and I just learned some new simulation software and how to do the device simulation, and how to change the concentration of every transistor, like Na and Nd. We can change everything, and this is not possible with Cadence. Like I was solely dependent on the Cadence thing. So in the Cadence we just change width and length, and then the fingers width, everything we change only these things. But with this course I learned like how we can change how we can implement like this NA and ND. We can change these things of NMOS and PMOS, and this was my best lecture among them. Like I was solely purpose of my choosing this course was only because of the transistor, because I love transistors, and I implement with transistors. So that's why with this course I learned a lot. Thank you so much, professor.